This is part 7 of the series Limits, and in this part we're going to start out with the concept of infinite limits. And what we mean by infinite limits is that a limit that goes to infinity. We talked about these a little bit before, but now we're going to formalize the discussion. The definition of infinite limits here, it's another one of those cryptic epsilon delta type definitions, but in essence that's all it's saying is that for any m that exists that's greater than 0 here, I can always find a value in here such that f of that x value is going to be greater than that m. And on the other side, for any n that's less than 0 that I can find, there's always going to be some value in here such that this value, f of that value, is going to be less than that number n. That's what this text is saying. The statement, the limit as x approaches c of f of x equals infinity, means that for each m greater than 0, for each value here greater than 0, there's some delta value, some distance here, such that any x value, any x minus c, any value inside that delta region evaluated on the function is going to be greater than m. And likewise, the same thing is going to be less than n. Now, there's an important note here. Remember, we said before that this statement, the limit as x approaches c of f of x equals infinity, doesn't mean that the limit exists. It's describing the unbounded behavior which denotes that the limit does not exist. Very, very important point. Don't get confused in thinking that because we're saying it equals infinity or equals negative infinity, that the limit actually exists. It doesn't. This is simply describing how it does not exist. All right, let's take a look at an example and see if we can analyze these. So we want to determine the limits of each one of these functions by analyzing these from the left and right hand limits standpoint. So I want to first let's take a look at the left hand limit of this function. So we want to talk about the limit as x approaches 1 from the left of 1 over x minus 1 squared. So what's happening as we approach x equals 1 from the left? That means coming at it from this side. That means x is going to be less than 1. So some number less than 1 minus 1 is going to be a negative value. And if we take that negative value and square it, it's going to become positive. So this number is always going to be positive on the left-hand side. If that's the case, as this gets closer and closer to 1, this denominator is going to become closer and closer to 0, which means it's going to go into 1 more and more times. So this value is going to be positive, and that positive number is going to be increasingly great. So this value going from the left to the right, the limit from the left, this is going to approach infinity. So we would say the limit from the left equals infinity. Again, it doesn't mean that it exists. It simply means that the limit from the left it's approaching infinity. It's increasing without bound. The limit doesn't exist. It's just increasing without bound. Let's take a look at it from the right. The limit as x approaches 1 from the right of 1 over x minus 1 squared. All right, what's happening here is now we're approaching from this side, which means x is greater than 1. Well, any number greater than 1 minus 1 is going to be a positive, but again, that's being squared, so this is still going to be a positive number. As this x gets closer and closer to 1, this denominator is going to become closer and closer to 0, which means it's going to go into 1 more and more times. So this is approaching infinity as well, and it's approaching positive infinity. So because both of these are approaching the same non-real value, as both of these are increasing without bound, we could say, it would be a legitimate statement to say, the limit as x approaches 1 of 1 over x minus 2 squared equals infinity. Therefore, it does not exist. Now, the only reason we could say this is because it's going in the same direction from the left and from the right. If it didn't, we wouldn't even be able to make this statement. We would simply say it doesn't exist. But because the function is increasing without bound from the left and the right, we can say it's increasing without bound, therefore it doesn't exist. All right, let's take a look at the next one. So here, we want to look at this from the left-hand side and from the right-hand side. So first, let's take a look at the limit as x approaches 1 from the left of negative 1 over x minus 1. Again, we're coming at it from the left-hand side. Therefore, this x value is always going to be less than 1. Well, if it's less than 1, some number less than 1 minus 1 is going to be a negative number. And a negative number divided by a negative number is a positive number. And so as this denominator gets closer and closer to 0, as x gets closer and closer to 1, this number is going to become closer and closer to 0, which means it's going to go into that more and more times. And because this overall fraction is positive, this is approaching positive infinity. Let's go ahead and take a look at this from the right now. Let's look at the right-hand limit. So the limit as x approaches 1 from the right of negative 1 over x minus 1. We're coming at it from the right-hand side, which means x is going to be greater than 1. So a number greater than 1 minus 1 is going to be positive. And a negative divided by a positive is going to be a negative number. Now, as x gets closer and closer to 1, this denominator becomes closer and closer to 0, which means it's going to go into negative 1 more and more times. And since the overall fraction is going to be negative, this value is approaching negative infinity. So the final result, since this is going positive infinity and this is going negative infinity, so from the left it's going up, and from the right it's going down. It's approaching two different unreal values. Therefore, we would have to say the limit as x approaches 1 of negative 1 over x minus 1 does not exist. That's all we can say, that this limit doesn't exist. Now, you may have recognized the fact that 1 in this function is actually what we used to call vertical asymptote in this function in pre-cal. Well, we still do. But these limit ideas give us a more formal description of what an asymptote actually is, so that we can put down a much more formal definition for what an asymptote is. And that's what we're going to do next, is take a look at what are vertical asymptotes. So here we're going to use the idea of continuity to describe vertical asymptotes. Let f and g be continuous functions on an open interval containing c. If f of c doesn't equal 0, this numerator is f, and g of c is equal to 0, this denominator function is g, and there exists an open interval containing c such that g of x doesn't equal 0 for all x not equal to c in the interval, then the graph of the function given by this rational expression has a vertical asymptote at x equals c. That's all it's saying, is that if there are two functions, f and g, and the denominator at some point is equal to 0, but at every other point doesn't equal 0, then this function has an asymptote at the place where this denominator function g equals 0. That's all we're saying. So let's take a look at an example here. In this first example, our top function f is constant, so it's always 1, which means it's not 0. And our g function, there is a value where this can equal 0. It's at -1. But at all other points, this bottom expression is not going to be equal to 0. So it satisfies this condition up here, that there is a point C where g of c equals 0, but all the other points are not equal to 0. And so we can say that this function has a vertical asymptote at x equals -1. And the easiest way to state that, or to find it, is to say, well, where is 2x plus 1 equal to 0? And by solving this for x, divide by 2, you have x plus 1 equals 0, x equals -1. But you should be able to look at this, plug in a -1, and see that that's going to go to 0. Either way you do it, it works out the same. So that's the analysis you go through, and we know that we have a vertical asymptote at x equals 1. So this is your vertical asymptote. Note, that's the equation of a line. X equals -1 is the vertical asymptote. So let's take a look at a couple more examples. In this top function, we have a sum of two squares. That can't be simplified, so we just rewrite that. But the denominator can be. So it's x minus 1 and x plus 1. Now we can see there are two conditions where this denominator is going to equal 0. One is at 1, and the other one is at -1. So we know that at x equals 1 and x equals -1, this denominator is going to equal 0. We know that there are other values other than 1 and -1 where this denominator expression is not 0. So that satisfies the definition of a vertical asymptote. And this is never going to be equal to 0 because you can't put a negative number in here. So this is always going to be positive. Therefore, our vertical asymptotes are x equals 1 and x equals -1. Now down here, for this function, cotangent is simply cosine over sine. We know that the period of cotangent is the same as the period for tangent, which is pi. So the period is pi radians. And if we take a look at where is this denominator 0, well, sine of 0 is 0. And so any increment of pi, the sine of pi is 0. The sine of 2 pi is 0. So at any increment of pi radians, this function is going to have a vertical asymptote. So we can say that there's a vertical asymptote at x equals n pi radians. So any integer factor of pi is going to give us a vertical asymptote. Okay, let's go ahead and work one more example. In this example, we want to determine the vertical asymptotes of the graph of this function. We have a quadratic on top and the difference of two squares in the bottom. So I'm going to go ahead and factor the numerator and denominator, and we'll start from there. So we have this set of factors on top, this on the bottom. We have a common x minus 2 factor here, so these go away, and we're left with x plus 4 over x plus 2. Now we can see that 2, x equals 2, is not an asymptote, it's a whole, because these factors canceled out. But here, the x plus 2 is still there, so -2 is still a vertical asymptote. This denominator goes to 0 at x equals -2. So that is our vertical asymptote. Well, that wraps up this session, and that wraps up this series. I hope it was helpful to you, and I hope to talk to you in the next series.